What does a Venus flytrap, an earwig's wings, and a grasshopper's legs have in common? They're all natural examples of energy being stored in one state and effortlessly changing into another state. What would it take for engineers to develop materials that do the same?
We're trying to generate a material that can do pretty cool stuff, but it's still simple stuff, but it can do it without almost any intervention.
This element has like two stable states. So it is stable in this configuration, also stable in this configuration. So currently this is in all the elements are in one configuration, and I can just trigger.
Andres Arrieta leads the Laboratory of Programmable Structures at Purdue University. Him and his team are working on something called metamaterials, which are materials that combine the best characteristics of individual materials to form one better material. These kinds of solutions are bringing ingenuity to a variety of industries, including robotics, aviation, and even architecture.
The specific work that we have been doing on metamaterials is actually trying to generate some properties that we called programmable, in the sense that we're able, after the material is being made, we're able to actually significantly change the behavior of it in a controllable way.
So can you give me some examples of how you do that?
We've been doing that by arranging in a network what we call bistable units. And these units are essentially just like the slap bracelets that perhaps we used to play with when we were young.
Like a snap band, a bistable unit is just that, stable in two different configurations. In one state, it has stored energy. In the other, the energy is released, often with a snap. Professor Arrieta's team began with a pop-up dome, 3D printed from thermoplastic polyurethane. By pressing with a finger, the dome would snap to become either convex or concave. When they printed a 3x3 grid of these domes, they began to see new behaviours.
What we do with connecting them is essentially creating a metamaterial that has many different possible configurations, and each of these shapes has associated to it a different mechanical property.
By pressing certain domes in or out, the sheets formed various shapes, the bistable domes combining to form a new metamaterial, which they call hierarchical multi-stability. What's more, the dome-based metamaterial is able to store energy.
So every time you switch one of these units from its as-made state to its inverted state, you have to put some energy on it, but that energy is stored in the material, and this is what makes it a metamaterial in a way, that you can really significantly alter the behavior of this material by playing with the local arrangement of these units.
They look really fun to play with, but how can tech like this be useful?
We have a bistable gripper that is internally pressurized, and then the domes are inverted, and then the energy that is saved into those domes and that causes the formation of the gripper, it's then there to hold onto an object without any more provision of energy.
The gripper is sprung-loaded by the inverted domes to close on an object in response to air pressure in the surrounding environment.
Many robots are in certain ways mimicking anthropomorphic constructions or some sort of animal construction, but then that means our actuator systems are very localized. So we would have a joint, and then there will be an actuator at the joint, and this actuator would only really extend our arms or change the angle, etc. But if we could make the arm in a way that it would store some energy, we could do the trick that we did with the gripper of using just one input, pressure, and just one control input, and then generate a complicated reconfiguration.
Storing energy in structures is a trick used all the time in nature. and Professor Arrieta and his team see no harm in stealing some ideas.
Insects are very clever in using their exoskeleton and their morphology to create functionality. For example, insects use this protein called resin, and resin is essentially a very good spring. So they store energy on their joints of resin, and then they release them very quickly. And this is one trick that insects use to, for instance, jump very high. So in a similar vein, we see that we can generate storage of energy in, for example, flexible robotics, and then this energy can be released quickly to generate fast movements. This is one application, and we have illustrated that on a previous work that we did on this insect called the earwig that has an origami-like wing that reconfigures very nicely.
The ability of an earwig's wing to quickly spring out from one state to another could be replicated in the designs of robots, packaging, spacecraft, and biomedical devices.
Okay, let me see if I've got this right. Your metamaterials store energy in order to quickly change so that they can respond or adapt to different environments. But how can they be also used to make simple computations?
So of course, the first computers were mechanical. The abacus is a very simple mechanical computer. If we were able to do some more computation at the edge, actually the skin of the machine itself, or the load carrying structure of buildings or bridges or aircraft, then we would be able to take a lot of the data that it's generated by the interaction with the environment and leave the computational power to really do high-level decision making.
It's not a crazy idea. Professor Arrieta and his team studied the Venus flytrap, an example of an organism that's able to perform a simple computation, responding mechanically to stimuli on the hairs inside its trapping mechanism.
If you touch two hairs in a small time frame, and the plant doesn't have a brain, doesn't have a neural system as we know it, but still this is a computation.
The hope is this could be replicated on the surface of an engineered structure or robot, pre-programmed to react to external stimuli and computing a simple movement, saving energy and computational power coming from elsewhere.
So if we could leverage these properties of metamaterials in terms of their ability to reconfigure, to change their properties, and even to conduct some simple computations, we would see machines that will have something akin to reflexes and something akin to instinct that would allow them to respond quickly and hence be able to operate in more chaotic environment and allow us to concentrate our resources to then create better performing machines by simplifying this complexity of the world.